Okay, well, with the PMF, uh, X is completely specified. This gives you everything. PMF tells you probability X is equal to any value, so it completely determines X. If two discrete random variables have the same PMF, they're essentially the same random variable. Now, what do we have with the PMF? So one thing is we know, so first of all, there's a notation thing to be clear about. We could write, when we compute probabilities, say, if we want to find the probability, say, X is in some range, some set. So say we want the probability X is in some set of numbers. Then this we could write like this. We would sum its PMF over all X that are in. So I would write something like this. Sum X in A of P of little x. Okay, so that says element of. I know it's hard to read, but that's what it says. So this is how we would approach such questions. Okay, if we sometimes you might see something like probability x is in A and P of x is greater than 0. This is really, don't let this bother you. Okay, just try to make sense of it from the context. It should be clear. This is sort of not necessary, I don't think. But it's a sum, so, we said it's defined on all reals. So if you're very fussy, you might want to think, well, that doesn't make any sense to take a sum. So, but if you reduce it to this and this, to both of these, then it does make sense, because x only has a non-zero probability of being a countable set of numbers. Okay, so because, let's write this down, because S is countable, I can enumerate it. It may be infinite, like it might be all integers or even bigger than all integers, but it can't be uncountable. So it has to be able to be dealt with a sum. Then the range, this implies the range of x is also countable. Okay? X maps every outcome in S to something, so at most, the range of X is the same as the cardinality of the range of X is the same as the cardinality of S, but it might even be less. It might map many of the outcomes to the same thing, for example, maybe all of them except for one or something like that. So you could have something, and you often do have things like that. So, yes. Okay, so I hope that's clear. So this mainly means we can represent probabilities that concern DRVs with sums. Maybe infinite, but at least with sums. So we have one thing. So property, this is from the axioms. We must have that the sum over all x, which we could just write like this, over x, or even over x such that the probability of x is greater than 0 of P of x, this must equal 1. And this should be clear. Again, I don't want to make these too long, so I refer you to the notes as well. And you should go back and see the notes if you want more clarification on this. Well, this has to be true because functions map their domain, has to map everything in its domain to some number, right? So suppose here is S, and every little S1, S2, maybe there are infinite number S3, get mapped over here to some value. This is the range of X. So these all get mapped. They have to. And maybe this gets mapped to the same one here. And maybe there's another one gets mapped to this one too. But so maybe I have X1, X2 in this example. Well, imagine this is it. This is all of them. Well, I know these probabilities add to 1. So that means these probabilities add to 1, right? So the probability that S1 union S2 union S3 union S4 is just equal to the probability X equals X1 union X equals X2. This is just equal to the sum over all X. Probability X is greater than or equal to 0 P of X. But this is equal to 1 here, right? This has to happen. All right, so probabilities have to add to 1. Satisfy the axioms, right? All right, let's go to expected value next. So we also have this notion with every, so the PMF completely defines the random variable, but we also have this idea about expected value. So we define, it's sort of a secondary thing, but we define E of X, called the expected value, to just be the weighted average over the range, X P of X. And if you want, you could write just X here, or you can write X P of X greater than 0 if you're fussy. And this is called the expected value of X. It's a weighted average. See the notes as well. Okay, so for example, we can look at some of ours now. So for example, if X is Bernoulli P, then E of X is equal to, well, I just sum over all the probabilities. So we'd have 1 times P of 1, probability X is equal to 1, plus 0 times P of 0, that's 0 obviously. So I just get P of 1, so it's P. Probability of a 1 is P. Okay, I could do a longer example. Let's do another example. Say X equals sum of 2 dice. Then E of X is just equal to, I take the weighted average again, so it's 2 times 1 over 36 plus 3, 2 over 36 plus dot 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 plus 12, 1 over 36, right? And if we do this out, you'd see each of these are 7. So are 14. So I get, but if I divide by 2, I get a 7, right? So then everything, if I group it that way, becomes in 7. If you do this out, you get that the expected value of the sum is 7. Right. Right. You can take it in pairs, and then everything is 7, right? So this is actually equal to 7 times 2 over 36. And then you take the next pair, you get 7 times 4 over 36, etc. Everything's 7, and then the probabilities add to 1. Okay. Another example is we could draw 2 cards from deck of 52 without replacing, and let X equal number of queens. Okay, well then X has a range of 0, 1, or 2, so the expected value is just, so E of X is just 1 times the probability X is 1, so it's just P of 1. The 0, 1 goes away, plus 2 times P of 2. So I need to calculate P of 1 and P of 2, right? I don't even need to really calculate P of 0. So probability X is 1, P of 1. probability x is 1 is equal to, it can happen two ways. I'm using conditional probability. I'm going to say the probability I pick a queen on the first card and don't pick a queen on the second plus the other. So probability I pick a queen on the first card is 1 in 13. And, right, 1 in 13. And then probability, the conditional probability that I don't pick the queen on the second card, given I picked the queen on the first, is, let's see, there should be how many cards left over that are non-queens? 48? Yeah, so 48 out of 51, right? 48 out of 51. Plus the probability I don't pick, so 12 13ths, and now I do pick a queen, so I have 4 queens out of 51. Notice these are both the same, 48. I get the same thing here. So when I reduce this, I get 32 over 221. And now what's the probability? What's P of 2? Probability x equals 2. This is equal to, well, I got to pick a queen. Only way to do it is pick 2 queens. That's a 1 in 13. And now I have a 3 out of 51 chance for the next one. So 3 out of 51. That's actually 1/17. So this is 1 out of 2, 2, 1. So E of x is equal to 32. 2, 2, 1 plus 2, 1, 2, 2, 1. Which is equal to 34 over 221, which you might realize is 2 over 13. Okay, we'll look at this again. The 2 out of 13 might seem curious to you because it is twice times the probability I picked the queen on the first. And we will look at this again in a second. If you did want to check that the probabilities add to 1 in this experiment, it's not hard. We'd have to compute the probability x is equal to 0, and you see you do get they add to 1. So check. P of 0. No queen, right? 12 out of 13, and then still no queen, so 47 out of 51. And this turns out to be equal to 188 over 21. And this is true, right? So then the sum px equals 1 plus 32 plus 188. Right. Okay,